Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm Pushmeet Kohli. I'm a researcher in the machine learning and perception group. And I'm talking about learning to make multiple predictions. So the first question is, why do you want to make multiple predictions? Why not just stick with the old sort of thing, just make one prediction, right? Or maybe sort of give a distribution, right? The problem is that most users, when they come to Bing or when they basically interact with our photographs, they need solutions. They need results, right? One result or two results or three results. And at the moment, the machinery is only to provide them one result, right? And this is about making, predicting multiple outputs available to the user. So let me give you an example. Suppose here is an image, and you wanted to segment this image in PowerPoint. So what you want to do is essentially cut out this bird from the photograph and paste it in some different context or in some other image. So what you could do is basically you can mark these sort of pixels saying red pixels belong to foreground and blue pixels belong to background. And what PowerPoint would do in that case would give you this sort of a mask, this sort of a result, and now you have segmented your sort of bird and you can place it in any sort of other image. So what is the problem? The problem is that this method fails. So why does it fail? It fails because of two reasons. The first reason is that the model might be misspecified. So what do I mean? The model that I was using for the previous image segmentation task is just a pairwise Markov random field. It just sort of encourages smooth segmentations. It doesn't know about objects. It doesn't know that the head should be connected with the feet. There's no connectivity higher order constraint in the model. Why is it that these factors are not included in the model? Because they are very hard to sort of do inference in or hard to do learning in. Right? So we used a very simple model which actually does not describe the state of the world just because we could do inference in it easily. And therefore you will get these sort of results, and therefore one single result of this model might not be good enough. So you might need multiple sort of shots at it. The second sort of reason why one single prediction might not be appropriate is the problem might be just ambiguous. So the user sort of comes in, marks these blue pixels as background, marks these green pixels as foreground, but now the system has to sort of reason about, did the user want to segment both trained coaches or a single trained coach? So if the result was a single trained coach, then this should be the result. If it was two trained coaches, then these two segments should be the result. Okay? So wouldn't it be nice if we can somehow create a pipeline or a machinery which could basically give out both these results or a set of these results? Okay? And now this is not limited to segmentation, it is sort of everywhere. So if you're thinking about any structured output prediction problem related to images, say deblurring or denoising, you could now give the user not just one deblurring or not one denoising result, but give them, say, 10 results, and the user can choose, right? So if you are sort of uploading your photograph on Instagram, now the app could just provide you 9 filters and in a 3x3 format, and then you can choose which enhancement you want for this particular image. There's no reason for just one enhancement. You could think about what are the best 9 enhancements that could be assigned or that could be sort of put for this particular image. Okay, so let's sort of recap how we actually make predictions, how we do structured output prediction when only a single prediction is required. So most of these models like the image segmentation model are just linear models, right? So you have a bunch of, you have a vector of weights and you have some linear sort of features. And then what you do is basically you train this model by empirical risk minimization. Okay, so you have your loss function, you sum it over your training instances, here's your ground truth, here's your model prediction, and now you're going to just minimize over the parameters W. You're doing empirical risk minimization. That's it, simple stuff. In fact, we cannot do this because this is a very difficult optimization problem, so people sort of use a upper bound, right? Sort of a structured hinge loss, right? They minimize this sort of surrogate risk rather than the empirical risk, okay? And this will give you a single sort of result. You have learned your score function, and then you will be able to sort of find out the y, which has the maximum score, and that is the segmentation or the image labeling result that you wanted. Okay, so suppose here is a score defined over this multi-dimensional, this hugely dimensional sort of y vector. This y vector corresponded to sort of, in the case of segmentation, a binary vector which is with the length of the number of pixels, right? So you have this huge sort of space of y's, and the score function is defined over that, and the best sort of solution is the best segmentation. Now, if you wanted to get n best, you will see that most of these segmentations are very close together. You might basically get segmentations which sort of differ from one another by just a single pixel. So you don't need that, right? In the case of the train example, so if you go back, in the case of the train example, you want these solutions which are very, very different in terms of Hamming distance, right, from one another. If you just think about the n best solution, what it will do, it will give you one result which is this and the other result which is just 1 pixel away in terms of Hamming distance. You don't want that. Okay, so what you might want is basically, instead of this, where all the 3 best solutions are tightly are nearby, you might want to basically get these best modes of the scoring function. But the point is, the scoring function itself was trained by minimizing the empirical risk, and thus it only meant that the best y under the scoring function makes sense. The scores for the other y's don't make sense if you don't think about the margin arguments for time being. Okay, so what are other ways to actually generate multiple predictions? What one could do is basically take the scoring function and just add noise to the weights, the parameters. Just perturb the parameters and then find the best sort of y's based on the new scoring function, right? The perturb scoring function, and you will get these samples. Okay, so that's one way to do it. But then you lose any guarantees now. I mean, if the scoring function was trained in a particular way, then you don't you lose sort of all guarantees here. But there are works in the literature which actually take this into account very nicely. Okay. So what perturbation should one use in this case? The approach that has been taken in the computer vision literature is, why not generate sort of solutions which are different from one another? So how do you specify different? So you will first find the solution which has the best score. So here's the first segmentation, for example. Now you will add in an explicit diversity term which into your score function, which says the next solution has to be different. Now, people who sort of are familiar with DPPs would know that there is this sequential sort of diversity term which basically says that the next sample has to be different. So you could sort of think of it in that sort of way, where you have an explicit term which says the next solution has to be different. What it does, it makes the optimization problem very, very hard. But still, people have sort of have taken this approach. So first you add this term, now you will get this solution, now you will get this solution, and so on. Again, why are we doing this? Because SY, the scoring function, was trained by empirical risk minimization, and the only guarantees are for the best solution under the loss, under the scoring function. There's nothing else that the training was doing. So we take a different approach, and we say, instead of making multiple predictions from one single model, So instead of sort of trying to reuse the scoring function in some way to basically generate multiple predictions, why don't you just learn multiple scoring functions and just choose the best from each scoring function independently, right? So this has the benefit that if you learn now multiple models, you could sort of just put them into a parallel architecture, and all these models will be generating solutions simultaneously. So you don't have to wait for the sequential sort of sampling approach. Okay. Yep.
So this is different from the perturb the parameters approach, because you're not sort of randomly perturbing the parameters,
Yes.
but rather you're
Learning.
training
Exactly.
separate models,
Absolutely.
using something else that's sort of different about the way they're being trained. Right?
Exactly. Exactly. So how do we train them? So this is a good point. So what we do is we define a set loss. Instead of our normal loss, we'll now say, let's have a portfolio of models, and our loss is the best loss under the portfolio. Okay, so we have these multiple models, and these multiple models are generating multiple predictions, and we will say that the loss that this portfolio sort of incurs is basically the minimum of the individual instances in the portfolio. Okay, so in this case, suppose there were 3 models, and this was the ground truth. So the first segmentation model produced this, the second segmentation model produced this crazy segmentation, and the third model produced this. So in this case, the loss would be the minimum of these 3 losses, and it would be 3.44. Am I clear? Okay. Okay. So now the question is, how do you minimize this set loss? So recall that even minimizing the structure output prediction problem in the earlier case was in itself very difficult. Now we are sort of thinking about a portfolio of these structured output predictors, right? So how do you do empirical risk minimization in this? So what we did was essentially sort of came up with this set hinge sort of loss, and basically decomposed it, and then had a coordinate, rewrote it in this sort of way, and then had a coordinate descent method in which you optimize these indicator parameters and then these model parameters. So let me give you a sort of intuition about how this is working. Essentially, what the model is trying to do, it has specified some models in the portfolio, say 5 or 6, right? It has said 5. There are 5 models which are in the portfolio. What it will do, it will say that each training example can only contribute to one of the portfolios, to one instance in the portfolio, right? So if you think about a greedy approach, you train the first predictor on the whole sort of with the whole training set, see which instances incur the highest loss, and now basically use those instances for the second predictor. Right? And then do the same thing for the third, fourth, fifth, and so on. Of course, that would be just one iteration. Now you can do basically, you can go back and reiterate. Okay? So essentially, you are partitioning your training data by sort of assigning training examples to different parts of your portfolio. Okay? So yeah, so you just repeat this process, and so just to show that this upper bound makes sense and this algorithm makes sense, you can see that the objective function, the objective that we were minimizing, it sort of goes down, and the training error goes down. Now training error here is the set loss, and also the test error goes down. Okay, so all sort of well till now. Now this is essentially the test error. And here are different baselines. So MCL is basically what we'll sort of refer to our algorithm. We'll refer to it as MCL. CSSVM, this red curve corresponds to sort of manual clustering. So I told you that essentially what the algorithm is doing is essentially partitioning the training data into different partitions, and then using the partitions to train parts of the portfolio. Okay. And the CSSVM is essentially saying, let's cluster the data first and then train individual instances. And you can see it's quite bad. The green one is basically the best used method earlier, where it was using just one model and then generating multiple solutions by putting in these explicit diversity terms. Okay, how much time do I have? Okay, so should I take 5 more minutes?
I have a question while
Yeah.
you're figuring it out. So essentially, I mean, it seems like what you're doing is the risk minimization analog of fitting a mixture model.
Exactly.
Right? Because you have the coordinate descent algorithm is
Exactly.
basically doing assignment to each of these experts, and the set loss is basically saying, well, you know, it's the loss of the expert that you've been assigned to. Which sounds great, but my worry is it's not. It doesn't seem necessarily the case that once you've done this kind of hard assignment, that the other experts are going to do anything sensible, right? They're sort of off the hook.
Absolutely.
Once an image has been assigned to
Absolutely.
another expert, they can produce rubbish.
Yeah.
And so it seems like there needs to be something else to get a diverse set of good answers in there rather than, yeah, okay.
So exactly. Exactly. So what your interpretation about mixtures of models is absolutely correct. What the technical contribution, in fact, is essentially how do you train, right? Was essentially the training part. We were not claiming in terms of that we were the first to do mixtures, learning of mixtures. So it's exactly sort of model mixture learning. And your point is absolutely valid that once you assign the training example, then the predictor is off the hook. It can do anything, right? So you can think about this. As you add in more and more predictors in the model, at one point, all the instances have been sort of taken care of, and the new predictors can now just roam free. They can do whatever they want, right? Because they're off the hook. Because all the instances have already been taken care of. The problem lies in empirical risk minimization. If you were doing Bayesian risk minimization, then this would not have happened, right? Because there would always be some mass which unexplained. But now we have sort of, because we are using empirical risk minimization, we are in trouble. So in order to sort of, so I should be doing Bayesian risk minimization, but I'm sort of doing it in a sort of crazy way by having an explicit diversity sort of regularizer. So now this explicit diversity regularizer, what it says, is not only do you want to sort of minimize the loss, but you have to be different from each other. So now all the sort of predictors are coupled, right? So you could, in fact, even put a DPP prior here saying that you have to be different from other people in terms of what predictions you make for each instance. So the results are good. I don't have time for it, but we can sort of explain them. I really wanted to go into one more. I just wanted to make one more point. So the example that I gave till now was in user interfaces where the user can choose, is an oracle and can choose between sort of k examples you sort of provide to the user. The second very nice approach that we have just used this for is inverting generative procedure. So suppose you have a 3D model of the scene, and you are given an RGB image and a depth image, and you are asked the question, where is the camera? Right? Where is the camera when it is looking at this image? Where is the camera in the scene? So this is a very, very simple model, a very, very simple problem mathematically. You are just trying to find the camera pose, which when rendered gives an image which looks like the observation. Right? So this is a general sort of inverse problem. The problem is that this minimization is very hard to do. So what Jamie and others have done is basically use a discriminatively trained predictor to actually just directly make the prediction. Now, the problem is that just making one prediction does not always work. So what do? We just learn a portfolio of these predictors. So instead of just training one forest, one discriminative pipeline, we will train multiple discriminative pipelines which try to do the same sort of thing, which try to minimize the set loss. Okay, so yeah, of course, this improves again the results. And I think I'm out of time, right?
1 minute.
Okay, so essentially, what this graph shows is that on the x-axis are the number of predictors, right? And each predictor is basically giving its guess to where the camera is. and then we will start from that pose and then minimize our inverse. We'll do the optimization that we just mentioned. And you can see if you choose the oracle, after you sort of minimize that this error, once you minimize this error, and you minimize this error with multiple starting points corresponding to the different predictors in the portfolio, and then if you choose the best one, then you get this performance. If you choose basically, and these are essentially generative models, right? And they give you different levels of accuracy. But you can see that as you increase the number of predictors, it all sort of increases. And all these sort of multiple proposals are done in parallel. There's no sequential thing about this. So thanks for listening, and these are the conclusions.